Okay, so 3.1 displacement, velocity, and acceleration. And this is in regards to the 2D plane. So it's not dealing with velocity and acceleration in one direction anymore like it was in the previous examples. So displacement and average velocity. So what is displacement? Now, it's the shortest distance between 2 points. Um, Two paths or the magnitude between a final and an initial point. So you display this as a vector with the magnitude and angle of direction. So then what is the average velocity in a 2D plane? It's the exact same thing, except it measures the velocity in the net direction, so the magnitude again. Um, and it's the same formula, which is the displacement, change in displacement over change in time. So it's important to note that displacement is a state function. And if you know thermodynamics, I guess, which is where I kind of learned it, or you're familiar with or if you're familiar with just terminology, state function is when the paths don't matter. So let's take a path here, and let's say this is y and this is x. And you can denote this as yards, miles, feet, but just make sure these are consistent. Actually, you don't even need to, but here we're going to assume that both are miles here. So let's start at the origin because it's going to make things a lot simpler for us. So let's say this car travels 3 miles to the right. So this is 3 miles. And then let's say it goes 4 miles up. And okay, let's try this out. So again, what does this look like? A right triangle, right? I used a 3-4-5 triangle, but you can use any triangle because the magnitude is just calculated using the Pythagorean theorem. So did we travel 7 miles? Well, we did if we measure the distance in terms of distance. If we measure it in terms of distance. But if we measure displacement, we actually only traveled 5 miles, and this angle is just going to be inverse tangent of 4 over 3. That's the angle here. So we travel 5 miles in this angle's direction. So that's how we denote displacement. So whenever we denote average velocity, it's going to keep the same angle as the displacement. So this vector of average velocity is always going to be in the same direction as what the displacement term on top was, the angle. And then we'll do change in time. So let's say we did this in 0.1 hours. And this is definitely not, actually, let's just change this into the metric system, which is meters per second. We'll just say we did this in 2 seconds. So 2 seconds, which means that we traveled 2.5 meters per second here. So does that mean that we traveled 2.5 this way and then 2.5 this way? No, it only measures the initial and final position. So that means first we traveled 2.5 here per 1 second, 2.5 here the second. Now this is slightly confusing because that's not actually the path we took, but that's how we measure velocity and displacement. So we displaced 2.5 in this net direction first, and then 2.5 in the next, which is what the average velocity calculates. And it's the same angle because it copies the angle from the previous displacement calculation. So as we know, the final average velocity, this is just the denotation. So we know that the final position equals the initial position plus change in displacement. And you denote this as r in the book, so it's going to be r vector of displacement is equal to the r0, which is the initial vector, plus the change in r. If we can rewrite this as the change in r is the final minus the initial position, as we know before, pretty common sense. So then if we had this, if we started here at 2, 0, and we have another coordinate that is 5, 0, that's 3 here, so 3, and then 5, 4, so 4 here, and then 5 straight down the middle. So then we only calculate the magnitude, which again is the displacement vector component. So it's the same thing as the change in r divided by change in t. Here we just rewrite this average velocity formula in its numerical construct, or not, it's a variable construct, instead of saying it in words. So Instantaneous velocity is the same exact idea. Nothing changes, except now we introduce a limit, or not really a limit, they say, but it's as t approaches 0 of delta r over delta t. So same exact thing here, except the delta t is becoming 0 because that means we're measuring how fast the car is moving at pretty much at an instant of time if time is barely changing between the 2 points. Average acceleration is the same idea, except it's change in velocity over change in time. Now this gets slightly confusing, so please listen. Yeah, please listen. So let's take a field again, and let's do really simple ones. So let's say we have, and I know my special right triangles, so I guess we'll just do 45 square root 2 square root 2, and we're traveling to meters per second at a net velocity of 45 degree angle. And then let's say, wait. So if this was the final velocity and initial velocity, that means the change is 2 meters per second minus 0 meters per second, because it's a state function and we're only measuring the distance between these 2 points. Yeah, but in other terms, you would have to do the vector calculation instead of just subtracting 0, because I only subtracted 0 because this doesn't contribute anything. But if it was another vector, like, let's say the initial velocity was here, and we calculate the triangle here, we would have to subtract this point by this point using the means of complement, so just calculating the x and y here, and square root 2, and then doing square root 2 minus y, square root 2 minus x, and calculating the change between these and these 2 points as a vector complement. So that's all it is. Average of acceleration is just going to be the change in velocity over change in time. But now we're introducing this as in terms of a vector or an angle direction, because now we can say that the change in velocity or acceleration was this much at an angle of this. Slightly a little complicated to understand, but that's the logic there. And we don't have an example here to show. So that was the logic of kinematics. Not kinematics necessarily, but just acceleration and velocity, which are kinematic components in the 2D plane. So